Today we are going to see the derivation part of density of energy states. The density of energy states can be defined as the number of available energy states per unit volume of the material within the energy interval dE. For this, the diagram can be drawn as here or as given here. Both are the same diagram. Here it is filled with colors. That's it. Look at the diagram. For this, we are going to assume a cubical metal piece. Let A be the side of the cube. Let A be the side of the cube. Then the volume of the cube is A cube. So the total volume of the metal cube is A cube. We are going to construct a sphere out of it, just like what is drawn here or as here. So of the same volume A cube, a sphere has been constructed. In this, we are going to find how many number of available energy states are there. Energy states of the electron. In the diagram, O is taken as the center point or the origin of the sphere, and then it is a three-dimensional sphere. Therefore, Nx, Ny, Nz are the three quantum numbers here which represents the radius can be taken as N here. Therefore, the quantum number can be used for finding the electron energy states of the sphere which has been constructed of the same volume A cube. Here the N represents radius of energy E. That is, to explain more about this diagram, if I am going to take this as origin, let us assume there are number of spherical shells here. Number of spherical shells. Assume it is 3 dimension. I am drawing not the circles here. It is 3-dimensional shells. There may be number of shells here. 1, 2, 3, 4, 5. In that way it goes on and on. I am considering any 2 shells. From the origin, I am taking this second shell is with the radius N, and the third shell is with the radius N plus dN. That is just like it is 1 millimeter for representing, and for example it is at 1.1 millimeter. So N I am taking it as 1 millimeter, just it is an example, and N plus dN as 1.1 millimeter. So in between this N and N plus dN, the difference is dN. Similar way, the energy of this second shell is E, and the next is E plus dE. This can also be considered as in between any 2 shells in the sphere. We are going to find the energy states, number of available energy states in between this energy interval dE and of this difference of radius dN. Now moving to the derivation part. The number of available energy states in the energy interval dE. We are going to derive this. Now I am considering the first sphere of radius N and energy E. The number of available energy states in this volume of radius n and energy E can be written as 4 by 3 pi n cube, being the radius n is taken here. That is, the volume of the sphere is 4 by 3 pi r cube. Instead of r, I am replacing that with the radius of the sphere concerned, that is n. Similar way, I am taking the another sphere of radius n plus dn. Similar way, the number of available energy states of this sphere of radius n plus dn is 4 by 3 pi n plus dn the whole cube. Then in between the number of energy states available in between these two should be considered. Therefore, 4 by 3 pi n plus dn the whole cube minus 4 by 3 pi n cube, that is the number of available energy states in n plus dn and the number of available energy states in the sphere of radius Vn is taken and it has been subtracted. Now we are going for the quantum numbers nx, ny, nz. We are going to consider only the positive values of the quantum numbers. We know about the quadrant. For example, if I am considering a circle, positive x-axis, negative x-axis, positive y-axis and negative y-axis. So here we are going to find the number of energy states. The energy considered here is positive, therefore always positive. Therefore here in this quadrant, if it is a circle, if it has quadrants, first quadrant, second, third and fourth, only one quadrant will have the positive integer value. In this diagram, there are three coordinates, three-dimensional sphere, nx, ny, nz. Therefore, we consider that the positive integers of nx, ny and nz will be in one octant of the sphere. That is, I have the third dimension here as z-axis, and similarly on the other side there will be minus z. Positive integer value is considered for nx, ny, nz. Therefore, in this 8 pieces, only one octant will have the positive integer value. Therefore, this diagram is drawn with this piece. One octant will have the positive integer value. The remaining, there will be one or two negative sides will be there. That is, if I am going to consider the second one, there will be a negative here and then here negative. On the other side I have minus z also. Therefore, if you consider this sphere, among the 8 pieces, any one will have the positive integer values of nx, ny and nz. That is, x, y, z will have only positive integer value that is considered. Therefore, in this derivation, it should be multiplied with 1 by 8 because here, irrespective of negative and positive side, the whole is considered, but here only it is multiplied with 1 by 8, one octant of the sphere. Therefore, 1 by 8 into 4 by 3, that is 4 by 3 pi is common here. and then n plus dn cube minus n cube. I have 2 here, therefore pi by 6 expanding n plus dn the whole cube, it is just like a plus b the whole cube. Therefore a cube plus b cube plus 3a square b plus 3ab square, and then I have minus n cube here. Cancelling plus n cube and minus n cube. Also we have dn. I gave you an example that dn here is the smallest difference. Therefore if dn is very small, just like this, I have taken here as 0.1, dn is that 0.1 mm as an example here. That is n plus dn is 1.1 mm, n is equal to 1 mm. This is an example. Then if dn is equal to 0.1 mm, dn square will be a small value and dn cube will be the very small value. Therefore we are going to explain here as, since dn is very small, the higher orders of dn, that is in this formula we have dn square, dn cube, can be neglected. Since dn is very small, the higher orders of dn can be neglected. So in this formula, even we are simplifying this. Then we have pi by 6, the remaining is 3n square dn. 3 and 6 goes twice here, therefore pi by 2 n square dn. We have the formula to find the number of available energy states of the electron in the interval dn and in the energy interval d. So the energy of the electron should be considered here. The energy of the electron. Therefore the energy of the electron in a cubical metal piece of side A is, I repeat it, the energy of the electron in a cubical metal piece or cube of side A is E is equal to n square h square by 8m a square. I am going to rearrange this formula. N square is kept on because in this formula we have n, only n and n square dn in this way. Therefore n square is taken on one side and the remaining is rearranged as 8 m a square e divided by h square. Then n is equal to, from this I can find what is n. So taking root of n, I'll get, that is the power half 8 m a square e by h square power half. So n is equal to 8 m by h square the whole power half, a square and power half is a and e power half. This is, I am taking this as equation number 2, and previously we have an equation here for density of energy states of the electron. I am considering this as 1. Then look at the formula here. The density of energy states is pi by 2 N into NdN. I am writing it in this way. Let this be equation number 1. So I have N here, value of N, and then I need NdN also. So N, the expression with N has to be replaced with the expression with E. That is why N can be replaced with this equation, and for NdN I am going to use this formula. So N square is equal to 8ma square by h square into E. This is the formula. Now differentiating the above equation with respect to E. With respect to E, I get 2n dn is equal to, all these are constants, cannot be changed, by h square, but E is d. So differentiating this, I get 2n dn is equal to 8ma square by h square into de. But in the formula, we have n dn only. Therefore, we are going for n dn is equal to 8ma square by h square. This 2 is taken on this side and then with d. Let this be equation number 3. Now, applying equations 2 and 3 in equation 1, we get, what is equation 1? Pi by 2 into n into ndn, to find the number of available energy states in the energy interval dE per unit volume. Therefore, pi by 2 n into ndn. This is the expression number 1. Expression number 2 should be substituted for this. N is 8m by h square, the whole power half, a into e power half. This is for n, equation number 2. And then n dn, this n dn is equation 3. 1 by 2 8m by h square a square into d. Now I am going to consolidate this 1 by 2 and pi by 2. So I get pi by 4. 8m by h square power half, here 8m by h square power 1. So it is just like 1 and then half. So we have a power m into a power n is equal to a power m plus n. So we have a power 1 and a power half as a power 1 plus half, which is a power 3 by 2. So here I am taking these two as 8m by h square, the whole power 3 by 2. Then a square here, I am writing it as a cube. Then e power half 15e. So we have consolidated this as pi by 4, 8m by h square, the whole power 3 by 2, and then a cube e power half d. So density of energy states for the volume a cube is given here. And then the density of energy states per unit volume. Per unit volume, that is, if a cube is considered as unit volume, then this is taken as 1. Therefore, number of available energy states of the electron per unit volume of the metal in the energy interval dE is pi by 4 8 m by h square the whole power 3 by 2 e power half dE. Now each energy level provides two electron states with spin up and spin down according to Pauli's exclusion principle. Therefore, this expression has to be multiplied with 2 because each energy level provides two electrons with spin up and spin down. This way. Therefore, we have 2 into pi by 4 8 m by h square the whole power 3 by 2 e power half dE. Now I am cancelling 2 and 4. I get pi by 2 here. Therefore, density of energy states is equal to pi by 2 8 m by h square the whole power 3 by 2 e power half dE. So this expression 4 gives how many number of available energy states of the electron or in the energy interval dE. Now to find the carrier concentration of the metal. Carrier concentration of the metal. The formula is N is equal to integral 0 to EF naught here Z of E dE and F of E. Here how many carrier concentration is how many number of electrons are present in the metal, that is N, capital N. This Z of E dE denotes number of available electron energy states and F of E gives Fermi distribution function. This is a probability function, the probability of distribution of electrons in the energy levels. So the general formula, the limit is in the metal at 0 Kelvin, EF is the maximum filled energy level. Therefore, the limit is considered as from 0 to EF at 0 Kelvin, the maximum filled energy level. Therefore, it is considered as EF naught. Substituting Z of E dE as equation number 4, I get N is equal to 0 to EF naught limits within integration pi by 2 8 m by h square the whole power 3 by 2 e power half dE and F of E is considered as 1. It is a probability function. Therefore, 100% the electrons are present in this energy level, which are all ranging from 0 to EF naught. That is within 0 to EF naught, the limit 0 to EF naught, the energy states are filled. Therefore, the probability function shows F of E is equal to 1. 100% filled is taken as 1 here. Therefore, instead of F of E, I am going to substitute 1. Then, integrating pi by 2 8 m by h square the whole power 3 by 2 e power half is the integration x bar n dn is x power n plus 1 by n plus 1. Similar way here, if n is considered as half, I am going to take e power 3 by 2 by 3 by 2. This limit is applicable here, 0 to ef naught. Then this 2 and 2 get cancelled off. This pi is 3 is taken over the other side. So I get pi by 3 8 m by h square the whole power 3 by 2, applying the limit ef naught power 3 by 2. So here this is the formula to find the number of electrons present in the metals per unit volume. This can be also called as carrier concentration, the concentration of charge carriers. If the Fermi energy level of the metal at 0 Kelvin Fermi energy at 0 Kelvin of the metal, if you want to derive that, in this equation 5, the rearrangement is ef naught should be kept on one side, ef naught power 3 by 2. The remaining can be taken over the other side, that is 3n by pi, 3n by pi, and then this is taken over the other side as 1 by, therefore I am writing it as h square by 8m the whole power 3 by 2. I want only ef naught, so I need only ef naught, therefore I am multiplying throughout with the power 2 by 3 because I need only ef naught. It is with the power 3 by 2 already. I need to nullify that, therefore multiplying it with 2 by 3 throughout the expression. So I get 3n by pi the whole power 2 by 3, h square by 8m, already we have 3 by 2 power, now with 2 by 3. So cancelling, we get h square by 8m 3n by pi the whole power 2 by 3 is equal to ef naught. So this expression 6, using this we can find the Fermi energy at 0 Kelvin for the metal. Then average energy of the electron at 0 Kelvin. Continuously we can derive this. Average energy. So we know the general formula. Average energy is equal to total energy divided by total number of electrons. In a metal we have electrons are the only charge carriers. So average energy of the electron at 0 Kelvin is total energy divided by number of electrons at 0 Kelvin here. So the formula to find total energy is how many number of energy states are available at 0 Kelvin into the energy of the electron. That has to be considered here. And then just now we have derived the total number of electrons in the metal, which is equation number 5. So denominator is known to us. We are going to solve for the total energy of the electrons at 0 Kelvin. Therefore, the total energy, I am going to solve this can be taken as the total energy. this is N, which is equal to 0 to EF naught. How many number of energy states at 0 Kelvin, and then with energy E. Number of energy state at 0 Kelvin is the density of states. Therefore, pi by 2 8m by h square the whole power 3 by 2 e power half dE. I have E also here because total energy is number of energy states at 0 Kelvin into energy of the electron. Then taking this pi by 2 8m by h square the whole power 3 by 2 out of the integration, and integral 0 to EF naught e power, this is e power half e power 1 e power 3 by 2 dE. Integrating this we get pi by 2 8m by h square the whole power 3 by 2 e power 3 by 2 plus 1 by 3 by 2 plus 1. So I will get e power 5 by 2 by 5 by 2. So I am writing that e power 5 by 2 by 5 by 2 with the limit 0 to EF naught. This is the total energy of the electrons. Then this 2 get cancelled off. This 5 is taken over the here. Pi by 5 8m by h square the whole power 3 by 2 EF naught power 5 by 2. Limit is applied here. So this is the total energy of the electron. Now let this be equation number 7. I am considering this as 7. Equation number 7. So we are here to find average energy of the electron at 0 Kelvin, and this is the formula. Average energy is equal to total energy of the electrons at 0 Kelvin divided by number of electrons. So E average is equal to total energy is here we have derived just now, and then number of electron is equation number 5. So I am going for substituting this equation 7 and equation 5 here. 7 by 5. Equation 7 is here. Pi by 5 8m by h square the whole power 3 by 2 EF naught power 5 by 2 divided by equation 5 is pi by 3 8m by h square the whole power 3 by 2 EF naught power 3 by 2. So just check it out. This is equation number 5. So we have cancelling the like terms. These two get cancelled off, and this is taken over the numerator, and the denominator of the denominator is taken to the numerator. Just like 1 by 5 by 1 by 3, it is 1 by 5 into reciprocating this 3 by 1, I get 3 by 5. Just writing it as 3 by 5, and then I have EF naught 5 by 2 minus 3 by 2. So 5 by 2 minus 3 by 2, I will get 1 only, 2 by 2. Therefore 3 by 5 EF naught. So this is the average energy of the electrons at 0 Kelvin. So in this derivation, we started with the density of states, number of available energy states per unit volume. Started with a metal cube is considered of side A, the volume is A cube, and then two shells, spherical shells have been considered The number of available energy states in between these two volume of radii n and n plus dn is taken, and then the positive integer values are considered here. Therefore, one octant is taken. Then we have cancelled the higher orders of dn. Then we obtain the value pi by 2 n square dn, and it has been rewritten as pi by 2 n into n dn. Then energy of the electron is taken as n square h square by 8m a square, and then we have substituted the value of n and n dn, simplified the formula and obtained the value applying Pauli's principle, exclusion principle. We arrived up to the equation 4. It is the expression for finding out number of available energy states per unit volume, because A cube is a volume, it is considered as 1. Then carrier concentration of the metal, number of electrons that is present in the metal. The formula is integration z of E dE into f of E. Then we arrived up to the equation pi by 3 8m by h square the whole power 3 by 2 EF naught power 3 by 2. Even we can proceed to find Fermi energy at 0 Kelvin of the metal. Then we found average energy of the electron at 0 Kelvin.